right, I'm going to show a demo of Geneva on latest version 1.37. What it's going to do is it's going to do a bunch of variations on 4 different jobs. It loads a table full of images of cats and dogs. It calculates a file size, it calculates the dimensions of those images, generates captions using a GPU model, and embeddings, optionally using a GPU to enable vector search. Now, the first thing I'm going to do is I'm going to load data. I'm loading the Oxford's pet dataset, cute cats and dogs, and there's an example. And then what I'm going to do is I'm going to set up a distributed execution environment so that we can run this in a distributed cluster and get efficiencies that way. What I'm waiting for now is this array cluster to enter. And what's interesting here is I've pulled in all these dependencies into my notebook, into my local environment. And right now what this is doing is it's picking them up and shipping them into the cluster environment so that my notebook environment and the code in there is exactly the same code that's going to run in the cluster. And it's going to take a few minutes to load, but when that's complete, we can start executing jobs. All right, so it's finally pushing up the content of those archives and those zips and pushing them up. So the cluster should be up and running shortly. There you go. It took about 4 minutes to spin up, but now we're getting to the job. So here we have two UDFs, a file size UDF and a dimensions UDF. And really all it is a Python function. We have a column in our table called image, you can see here. And I'm loading it, I'm getting the length, and returning an int. That's all I really need to do, is wrap it with that UDF. Similarly, this is an image, so I'm using the library to open it up, read it, and get the size to get the width and the height. So here's my table. All I need to do to create a new column, a new computed column, is to add columns. So the file size is the new column that I'm adding, and it's using the file size UDF function. Dimensions is a new column, and it's using the dimensions UDF function. So when I look at the data, I see the original data that I had in these two new columns. File size, everything's empty, and dimensions is empty. And now all I really need to do is backfill. So there's a function here called backfill that's associated with the table, and I just named the column. Now I'm setting an option here for batch sizing. Basically, there's some checkpointing and there's some distributed system stuff going on behind the scenes in order to make it so that we don't have to duplicate work. So I've set the batch size to 10 here in order to make it, checkpoint the result every 10 entries. Now, this is spinning up a cluster right now and spinning up worker nodes. So the first run usually takes about 2 minutes for it to warm up. All right, my workers have started, and now you can see things talking about rows checkpointed, rows ready for commit, and rows committed. And we'll kind of see them all kind of make progress. Rows checkpointed is basically how many of the rows have had the UDF applied to it, and the values saved off and checkpointed so that we don't have to recalculate it. Rows ready for commit. Behind the scenes, Lance has partitions called fragments, and this is how many fragments are basically ready to be committed to the table. And then rows committed is the number of actual rows that have been committed into the table. And we'll dig into that a little bit more in the next example. So this one took about 3 minutes, and you can see that all the file sizes have landed. The next job is doing dimensions, and I've added one other parameter, commit granularity. So same story, now I'm running this calculation, and then every 5 fragments, a commit will happen. And that will basically say, these are now visible for reads. And we're doing 5 fragments, there's about 25 rows per fragment, so you'll see this go up 125, 125, 125. So nice progress being made, and this took 42 seconds, much better because all the nodes have been warmed up and are ready to go. The next thing I'm going to show is a vector embedding pass. In vector embedding, we actually use a model. So we're going to use a stateful UDF to capture this computation. The setup is the thing that actually loads the model, and we want to load it only once. So we have a guard function in the inner loop so that we load the model once and then just pump the images through. Same story, we add an embedding column called gen embeddings. And this time we're going to kick it off using an async backfill. So you'll notice it only took 2 seconds, and we have an empty column here, and I have a future. Now this is a loop that's going to check on the future every 5 seconds and report on how many rows have been written out. So you can see here, initially it is empty, and now it is actually starting to do some processing. Now we have some rows ready for commit. And once we have the commit granularity, we'll start seeing things. And there you go. We've committed 100 rows so far, and we're currently at version 35. A few more seconds later, and we've got more commits with more data landing. And there you go. We have our embedding column set up. We have all 500 versions, and you can see the versions have incremented. It took about 1 minute and 30 seconds to finish. And now we have embeddings. It's great. What do we do with embeddings? Well, what we want to do is we want to do a vector query. So I'm going to kind of use this model again, load it into the GPU in order to look for a Chihuahua image. So here, these are different queries. I'm going to feed it to my tokenizer and get a vector that I can do a search on. And then I just use LanceDB's search mechanism with the vector on the embedding column. I get 10 rows, and I'm just going to spit out the first image, and voila, I actually got the Chihuahua that I was looking for. Right. All right. The next thing I'm going to do is a captioning job. Now, this job actually uses the GPU, and it uses this particular model from Hugging Face. I'm going to first show the optimized stateful UDF version. Then the idea is very similar. What I'm doing is I am loading the model with a setup function, and then I have a guard function, and I just pump the images through one at a time. The interesting thing now is this annotation actually has a CUDA equals true. This says, I need GPUs in order to run this. So right now we're waiting for GPUs to spin up so that we can actually get the work done. But then we do exactly the same thing. We add a new column. We'll call it caption blip v2, gen caption. So that's my UDF. I've got my new column here, and it's empty. And I will kick off an asynchronous job to try to run that and have a low commit granularity. So we're actually going to wait here for quite a bit because oftentimes we get blocked waiting for GPUs, but we'll come back when we have them. All right, we're starting to see this number tick up, and now that it's going, it should start moving relatively quickly. And this is where the commit checkpointing really matters quite a bit, right? Because this is expensive work. It's using the GPU, and we're able to partially commit and partially add data. You'll notice that the first commits have showed up now. So when I scroll down, I should be able to get a sample of the data. There you go, 50 rows committed, 100 rows committed, and we can see the version numbers ticking up as we make progress. So there we go, the job completed. So we actually spent most of our time waiting for the resources in order for the job to execute. And now we have our captions all present in all these columns. And what we can see here is we can see the history of the jobs, right? So we've had several backfill jobs and several of them are done. One of them failed. So we have different statistics and different information about these jobs. Now I'm going to show you something else that's pretty interesting. Concurrently executing jobs. So here is our table as it last did. And what I'm going to do is I'm going to use those exact same functions, except I'm going to create the same columns but with a new name, all with async. And what we're going to do is we're going to run them all asynchronously in concurrent. We're going to run them asynchronously and concurrently. So here is my new table, and I've got my 4 new columns, async, 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 and all the values are null. I'm going to dump the schema. You can see the UDFs attached to those columns. And I'm going to run backfill on them. And, here this is already completed. It took 37 seconds to complete. And you'll notice that this async column has been filled in. The second feature is complete. It took 5 seconds. A lot of that work had happened already. It's landing here. The next job took 39 seconds. That's all the captioning. And 6 seconds to do the embeddings. Yep, there's the embeddings. Great. All right, one more demo. We're going to use blobs. So oftentimes for large media things, what we want to be able to do is use a blob encoding so we don't have to read all the data. And we want to write things out in blobs because we might be writing out things that are fairly sizable. So what we're going to do is we're going to take the image column and we're just going to return it. But now it is a Lance encoding blob true. So this is being saved off as a large binary. I'm doing a type conversion. And you can see the job just finished. I add a column, I run the backfill, and now I have a new column in my table. And it's just reporting the metadata about the image. So it's an offset and the actual blob data. So that's an example of us writing a blob. Similarly, you can use a UDF and have a blob file as the input. And I'm just going to read it, get the length of the files, but I'm actually going to use the blob API to do it. So I create a length log image blob, and the job is running. And it commits and completes. And I have my new image length column. Now, after all that work is done, I go and shut down the cluster.